Good evening, everyone. My name is Odongo Emmanuel. I am going to take you through my presentation on machine learning. Those are my particulars, as you see in that slide. My registration number, as you see here, and my email. So straight away to begin with, allow me to take you through my slide 2. My slide 2, and that is introduction to machine learning. Basically, I have to talk about the definition. Machine learning is a field in artificial intelligence that allows computers to learn from data and improve their performance without explicit programming. Here, you look at the data. It is either in the form of labeled data or unlabeled data. It is labeled data in the way that you can have maybe information about something and it is tagged so that the machine can understand the meaning of that something you have. Or it is unlabeled so that it can predict its outcomes. So the core ideas with machine learning here, it replaces static instructions with dynamic data-driven predictions. The static instructions here, these are instructions that limit access to files. So it replaces such instructions with dynamic data-driven predictions. The dynamic data-driven instructions here can be the continuous changes in data as they predict the future outcomes on the inputs. Then we look at why it is important. Powers applications like self-driving cars, recommendation systems, and voice assistants. Now, these self-driving cars, you can have an algorithm or develop an application that has an algorithm that is in position to maybe drive a vehicle without the need or knowledge of a human being, or without a human being being in position in the steering. That is what I was meaning there. So basically, let me take you through the types of machine learning. As you can see them there, we have supervised learning and reinforcement learning. Looking at supervised learning, it uses labeled data to predict outcomes. Example, house price predictions. The labeled data here are labeled data. I can talk about labeled data. It is data that has been assigned specific categories. The categories or tags, allowing a machine learning model to understand its meaning. Get it? The type of data that has been assigned specific categories or tags, allowing a machine learning model to understand its meaning. For example, you can have a picture of a cat. You can have a picture of a cat, and it is named a cat, meaning that picture has its meaning as what? A cat. Or you have a new building, but with a label on it having that house to let, meaning that building it is specifically for rent. That is a day-to-day life example. Then I can also talk about maybe the location of a certain building. When you talk of house prices, take for example in our day-to-day life, if you want a house like for example in Munyonyo, you know Munyonyo is a place of high-class people, so you can easily predict the prices of houses in Munyonyo being high compared to the prices of houses maybe for example in Bukoto, here in Chikoni. Then unsupervised learning identifies patterns in unlabeled what? It identifies patterns in unlabeled data. Unlabeled data, this is raw data. It is raw data without any assigned levels used or tasks where the model needs to discover patterns on its own. The machine learning model has to identify patterns on its own. Now, an example here can be a collection of images without any information. That's like I talked about the cats or how a new building. So you can have a collection of maybe cats without any meaning about them, what it talks about. Maybe a new construction site when you don't know what it is all about, either it is for rent or it's a commercial building or it is for shops. You get it? That is what I'm meaning. Then reinforcement learning trains agents to make decisions by maximizing rewards through trials and try and error. You get it? You try and error. When you try and it goes, that is all. That is it. When you error, next time you learn from the what? The error. The machine learning process, it has a series of steps. The first step is data collection, gathering relevant data sets. You get the data by maybe making a questionnaire to know about certain, to answer to a specific problem you're addressing to as you're developing the algorithm. Maybe the problem can be the issue of absenteeism. Take for example absenteeism. Then you decide to get a solution, and the solution among it may be a biometric machine that takes fingerprints or facial recognition. So you need to understand the problem. You first collect data. You collect data on how reliable is that biometric machine if it is introduced, and how does it address the what? The problem at hand. Then processing, handling the missing values, and normalize and scale the features. The missing values can be maybe what other solutions are missing in the what? In the solution you've tried to develop in a given what? Problem. Then model selection, choose an algorithm based on the what? On the problem. That one is self-explanatory and direct. Then training, fit the model to training data. You have to train the data maybe by trial. Try and see how accurate it is. How is it answering the problem? Addressing the problem that you are trying to work on. Evaluation, that is testing performance on unseen data. That is testing. You have to test, give a period of testing. Then you assess maybe by printing out the results. Maybe if the biometric machine runs for a week, you have to test by printing the results and see how many absentees have you captured. How reliable is the system? The key points here is processing is critical for model accuracy. Linear regression. When you talk about linear regression, it is a model. It's a model that estimates the linear relationship between a scalar response, that is the dependent variable, and one or more explanatory variables, the regressor or independent variable. So here, it is simply, in a brief, it is a model with exactly one explanatory variable. A model with one explanatory variable. Now, a model with exactly one explanatory variable is a simple linear regression. A model with two or more explanatory variables is a multiple linear variable. So the term is distinct, and it has the equation as you see. The key concept here is uses the least sequence methods to minimize errors. Application is predicting trends. Example, the stock prices. Then maybe scale forecasting by maybe looking at the methods that can easily be help in forecasting the future stock prices. You get it? That is all about linear progression. Then we look at the what? The key nearest neighbors, classifying data based on the majority vote of key closest neighbors. You get it? The overview is all about classifying data based on the majority vote of key closest neighbors. Now, when you talk about in statistics, the key nearest neighbors algorithm is a non-parametric supervised learning method. It is a non-parametric let me quickly talk about linear regression. Let me talk about the linear regression. Linear regression, these are models. Okay, it's a model. I beg your pardon. Linear regression is a model that estimates the linear relationship between a scalar response. Those are the independent and the dependent variables between a dependent variable and one or more independent variables. Now, linear regression is in two forms. It is in the form of a simpler linear regression. That is a linear regression with one explanatory variable. Then it is also in the form of multiple linear regression. A multiple linear regression is a linear regression with two or more explanatory variables. It has the equation as you see it here. Then the key concept here about linear regression is that it uses the least square methods to minimize errors. The application here, it predicts trends, example the stock prices, the sales forecasting. Then let me talk about the key nearest neighbors. The key nearest neighbors. This is a key nearest neighbor is classified as data based on the majority vote of the key closest neighbors. It is a non-parametric supervised learning method, and this method was was developed by Evelyn Fix and Joseph Hodges, and later it was expanded by Thomas Cavers. This KNN, it is used basically for classification of data, the output of which is a class membership. That's all about linear regression. It has a distant matrix, the Euclidean distance, that is a straight line distance. These are the concepts that we looked at in mathematics. Maybe I can say refer you to our high school experience. Then the Manhattan distance, that is the city block distance. Application, it is text mining. It is applicable in text mining, agriculture, and in finance, predicting the future outcomes of what? They take, for example, in the Forex Bureau, the changes in the what? In the dollar rates. So it is used in classification and predicting what? Future changes in the prices maybe. The challenge with it performance declines with the larger data sets or irrelevant features. Larger data sets makes the performance to decline because they are heavy. Then let me take you through decision trees briefly, how they work, and the key metrics. A decision tree is a flowchart-like diagram that shows the possible outcomes of a series of decisions. So the key metrics here, how does it work? How do the decision trees work? The decision tree starts with the root node. It starts with the root node. Then each branch represents a possible action or a decision. So it follows a certain branch until it gets to its output. You get it? So it splits the data into branches based on the feature values until outputs are classified. The key metrics here, we have the gene impurity, measures misclassification probabilities. Entropy measures information gain. You get it? Strength is all about, it is easy to interpret and handle both numerical and categorical data. The limitations is sensitive to noise data and prone to overfitting. Then let's talk about the random forest. When you look at the random forest, it is a machine learning algorithm that combines multiple decision trees to make predictions. It combines multiple decision trees to make decisions. You get it? How does it work? It creates the decision trees during training. Training the algorithms creates many decision trees, each trained with a random subset of the data. Then it makes predictions. Each tree makes its own prediction. Then it combines the predictions. The algorithm combines the prediction from all the trees to get the final results. Looking at the average predictions, what are all those things. Applicability, it is applicable on fraud detection and image recognition. Let's look at clustering with k-means. The concept is all about grouping data points into key clusters based on similarity. The algorithm has about 3 steps. That is random initialization, centroids, assign points to the nearest centroids, recompute centroids internally. Application, it is applicable in image compression. You get it? If the images are bigger, for example, it can be applied in compressing such images to be light and easier to move as a data. The challenge is it is sensitive to outliers and initialization. Let me talk about the principal components analysis. It reduces them dimensionally while retaining variance. How does it work? It computes principal components that represents the data, discards insignificant components to simplify data sets, the components which are not important. Applicability, it's applicable in facial recognition, data visualization, among others. And it is limited. Limitation assumes linearity and loses interpretation. Let me talk about ensemble techniques. That is bugging, reducing variance by training models on bootstrapped data. Example, the random forest that I have talked about. The bootstrapping reduces bias by sequentially improving the weak learners. That is by you understanding where the problem is. It is able to tell you by underlining, maybe putting it on red, so that you can go back and do debugging. Key benefits: combines multiple wiki models to produce a robust predictor. Application is applicable in predictive analytics, the GAGO competitions. Then support vector machines, separates classes with the maximum margins using a hyperplane. The key concepts here is the kernel functions map data into higher dimensions for better separation. The margins, key distance between the hyperplanes and the nearest data points. Applicability, you see it on text classifications, image analysis, to mention but a few, even in biometric machines that I talked about last time. Application and feature trends. You have application, you have things like healthcare, finance, and retail. These are the application. And the feature trends, you have the ethical, artificial intelligence, and bias reduction. The real-time processing with the Internet of Things and edge computing. So that is basically my small presentation on this. I thank you so much for listening and thank you for your attention.